Okay, let's do the extra practice problems for chapter 13. Number 1, 75 kilogram sample of lead starts out at 16 degrees, it ends up at 24.1 degrees. How much energy was involved in the change, and did the sample gain or lose energy? Remember, if the Q is negative, it loses energy. If it's positive, it gains energy. And so we are going to use the energy equals the mass, the specific heat capacity, and the times the change in temperature. And so in this case, we are looking for the energy. We are given the mass at 75 kilograms, but this is in grams, so we have to put the 75 kilograms in grams also. I'm going to be really bad and make it grams just by doing that. And then C is 0.160 joules, grams, degrees Celsius, and then the change in temperature, delta T equals, remember it is the final minus the initial, and the final temperature is 24.1 degrees Celsius. Make sure you put them in the right places. It makes a big difference. And its starting temperature was 16 degrees Celsius. That equals 8.1 degrees Celsius. So I'm going to put it here, 8.1 degrees Celsius. Now those two significant figures are going to limit what this overall answer will be. When you multiply this all together, notice the grams will leave, the degrees Celsius will leave, and you will be left with, what comes out of my calculator is 97200, and that would be joules, but I can only have two significant figures. So I'm going to lose this 2 and make it this. So Q equals 97,000 joules in this particular case. And because this is positive, because this wasn't a negative number, so this was positive, that means that the object gained this energy. So your other answer there, and make sure on your test you answer everything he asked for, so make sure you put gain there. Number 2, 150 grams of water in a liquid phase gains 1,600 joules of heat. If it started out at a temperature of 25 degrees, what is the final temperature? Okay, so here, once again, we have Q equals mc delta T, and we're given that it loses 1,600 joules, and, oh, it gains 1,600 joules. That made a difference. I was about to put a negative there, but it gains 1,600 joules. We were told that it's 150 grams. We have memorized the specific heat of water, 4.184 joules per grams degrees Celsius. And we know that this is the final temperature minus the initial temperature, and we're looking for the final temperature, and we started out with the initial temperature of 25.0 degrees Celsius. So if we go ahead and we're going to try to get T by itself, so I'm going to divide both sides by these guys. So if I divide both sides by these guys, at 4.184 joules per grams degrees Celsius, and I divide this side by the same thing, because that's what I can do, is the same thing on both sides, we end up with this. And so if you go ahead and do the math on that, two significant figures, 2.5 grams leave, joules leave, and I'm left with degrees Celsius. Okay, so that equals 2.5 degrees Celsius, because that didn't leave. Okay, the other guys did. So now we can go over here, and we know that 2.5 degrees Celsius equals the final temperature minus the initial temperature. Okay, so then when you go ahead and solve that, it's going to give us a final temperature of 27.5 degrees Celsius. That would be the final temperature, and that's why. Number 3, 17.8 gram sample of an unknown metal loses 1.2 kilojoules of heat. The metal's temperature lowers, and that gives you the temperature change. What is the specific heat capacity of the metal? Once again, we're doing Q equals mc delta T, and if you write that every time, you'll have it memorized in no time. We are looking for C. I'm going to go ahead and solve for C. So Q over m delta T. Okay, so Q we're given in kilojoules this time, And this has to be in joules, because remember the specific heat is joules per grams degrees Celsius. So I'm going to take the 1.2 and I'm going to make it times 10 to the third, and that would be joules, over the mass we're told is 17.8 grams. And the change in temperature, remember it's the final minus the initial, and we're told that the final temperature is 24.6 and the initial temperature is 94.3. And so that's going to give us a change in temperature of negative 69.7 degrees Celsius. So I'm going to put my negative in here. Make sure you do. Because what does that tell us about, it loses, this should have been negative too, right? Because I can look at that and tell. Because this has to be a positive number. So this was losing temperature, so it gets a negative. This, when you do the final minus the initial, gets a negative. And therefore the two negatives will make a positive. We have two significant figures. So C has to be in two significant figures. And it's going to be 0.97 joules grams degrees Celsius. I just take these and put them here. And the good news is that works because we're looking for the specific heat capacity. Number 4, 150 gram sample of metal is heated to a temperature of 100 degrees, put in a calorimeter, contains 250 grams of water. If the water's temperature rises, and it tells you the change in temperature, what is the specific heat capacity of the metal? Ignore the calorimeter in your calculation. So here we have negative Q of the object equals the Q of the liquid, which in this case is water. So that means negative MC delta T of the object equals MC delta T of the liquid. Okay, so and we are looking for here, please remember this is Q of the calorimeter. But we are ignoring the calorimeter in this case, so we dropped it out. And we are looking for the heat capacity of this object. So if we put these in here, we have negative, we have a 150 gram object. We're looking for C. And the change in temperature, it says it started at 100 degrees, so that's its initial. And it ended at 28 degrees because everything ends at the exact same temperature. And so that's going to give us a negative 71.9 degrees Celsius. And so we're going to put in here negative 71.9 degrees Celsius. Okay. Equals the mass of the liquid, which is water in this case, 250 grams. We know that water is 4.184 joules per grams degrees Celsius. And we know the change in temperature for the water was from 28.1 degrees Celsius to 24.4. Excuse me, it started at 24.4, it ended at 28.1. I wrote it correctly, I said it wrong. And so this is going to give us a change in temperature of 3.7 degrees Celsius, and that's positive, 3.7 degrees Celsius. Okay, so now we have all the numbers in here that we can. And when you do this, please notice this has two significant figures. I'm going to divide both sides by the E to get my C by itself. So what I'm going to do is come over here and I'm going to make this positive because of the two negatives, and I'm going to put my 150 grams over here and I'm going to divide by my 71.9 degrees Celsius here. Notice that this will leave, and I'll be left with this, which is what I need because I'm trying to find a C. This will be limited by two significant figures. So C will equal 0.36 joules grams degrees Celsius, because that's what's left is this. This limits us to two significant figures, and so that's what we have there. Number 5. A 115 gram sample of glass is dropped in the calorimeter that contains 150 grams of water. If the water starts out at 24 degrees, goes to 29 degrees, what's the initial temperature of the glass? We're once again ignoring the calorimeter, but just for practice, Q of the object equals, negative Q of the object equals Q of the liquid plus Q of the calorimeter. All right, we are ignoring the calorimeter because he was kind and showed us grace. And so we know that MC delta T of the object, the negative, equals MC delta T of the, are we working with water here? Yep, water. So I'm just going to put liquid. Okay, and here we're looking for the initial temperature of the glass. All right, but we're going to go ahead and start plugging things in. So we have 115 grams negative of glass. We're given C, 840 joules, grams, degrees Celsius. And the change in temperature is actually what we're looking for, the initial temperature of the glass. But the final temperature of everything's going to be the same, so it's going to be 29.0 degrees Celsius minus the initial temperature. And then we have to do the liquid over here. We're told that we have 150 grams of water. We know water is 4.184 joules per grams degrees Celsius. And we're told that it goes from 24 to 29. So 29.0 degrees Celsius minus 24.0 degrees Celsius gives us 5.0 degrees Celsius. That's our delta T. There we go. All right. Now, what we're going to do is let's divide both sides by these that are multiplied onto where our variable is. And so we've got a negative 115.0 and 0.840 joules per grams degrees Celsius. And by my dividing them by both sides, I can get rid of these. Okay, we've got two significant figures here, so when you do this, you end up with, over here, I want you to notice, this will cancel with this, grams and grams. You'll be left with degrees Celsius, and what you get here in two significant figures is negative, because of this negative sign, 32 degrees Celsius. And this still applies, so 29.0 degrees Celsius minus the initial temperature equals negative 32 degrees Celsius. And so with that, you can add this to both sides, add this to both sides. So the initial temperature equals 61 degrees Celsius. So we just plugged everything in and solved for our variable. That's what we did. Remember, everything has the same final temperature. Number 6, an object has a heat capacity of that. If it starts out at 25.1 degrees, ends up at 45.7 degrees, how much energy was involved in the change? Did the object gain or lose energy? Okay, so for number 6, we're going to use Q equals C delta T, because here we are given its heat capacity, not its specific heat capacity. So remember, this is for the whole object, not for a given mass. So it starts out, we're going to find the change in temperature. It starts out at 25.1 degrees Celsius and it ends up at 45.7 degrees Celsius. So that's final minus the initial. And so that's going to give us 20.6 degrees Celsius. Okay. The heat capacity, which is C, is 11.1 joules per degrees Celsius, and then the change in temperature we calculated at 20.6 degrees Celsius. So that will leave us an answer in joules in 3 significant figures, and so that's going to give us 229 joules. And because it's a positive number, we know that it is a gain, and you will have to answer that part. Make sure you don't forget to answer that. Number 7, 250 gram sample of a metal is heated to 125 degrees, dropped into a calorimeter. It has a heat capacity of 1170. The calorimeter contains 25 grams of water, initial temperature of 24.4 degrees Celsius. If the water's temperature rises to 28.5 by the end of the experiment, what is the specific heat capacity of the metal? All right, here we're doing negative Q of the object equals the Q of the liquid plus the Q of the calorimeter. And we're not told to ignore the calorimeter in this case. So remember, this is the negative MC delta T of the object equals, here we are given, okay, the MC delta T of the liquid, which in this case is water, plus, here we're given the heat capacity of the calorimeter. Remember, Q equals C delta T, doesn't it? Q of the calorimeter is going to be C of the calorimeter times delta T of the calorimeter. Because we're given the heat capacity, we are not given the specific heat capacity. Okay, so that's how we get the Q there. That's just that, because of what we were given. Okay, so let's start plugging in. So we have negative 2250 grams of a metal. We're trying to find the specific heat of the metal. Its change in temperature on the metal, the final temperature is 28.5 degrees Celsius minus the initial temperature, which is 125.0 degrees Celsius, equals, and so for number 7, negative 96.5 degrees Celsius. So I'm going to put in here negative 96.5 degrees Celsius. Okay, we've just done that. Equals, okay, the mass of the water, 250 grams times 4.184 joules per grams degrees Celsius, and the change in temperature of the water. The final temperature of the water is 28.5, and the initial temperature of the water is 24.4, 4.1 degrees Celsius, so we're going to put that in here. Okay, plus the calorimeter. We're told that the calorimeter has a heat capacity of 1170 joules degrees Celsius, and the change in temperature on the calorimeter is going to be the same as the liquid. We were told that in a pink box, weren't we? Okay, now we want to get everything on this side done, so let's go ahead and do that. 2 significant figures. Joules plus 2 significant figures, joules. So, and obviously that was not what I got in my calculator. I had to round up to that to keep it at 2 significant figures, joules. Okay, so this side is 9100 joules, this whole side. Now I've got to divide it by these two, don't I? Negative, well, these are a negative and a negative, so that's going to be a positive. So I'm going to leave out the negative sign because those two make a positive. There we go. And we have 2 significant figures, so our answer has to be in 2 significant figures. It ends up being 0.42 joules per grams degrees Celsius. So we just plugged everything in, watched our significant figures, took it step by step, and we were able to solve for that. Looks terrible, but it's doable. Number 8. A 27-gram sample of silver is heated to 100 degrees, dropped into a calorimeter whose heat capacity has not been measured. The calorimeter contains 30 grams of water at a temperature of 25.3 degrees Celsius if the final temperature is 28.5 degrees Celsius by the end of the experiment. What is the heat capacity of the calorimeter? So once again, we have negative Q of the object equals Q of the liquid plus the Q of the calorimeter. In this case, it's MC delta T of the object, remember it's minus, equals the MC delta T of the liquid, plus in this case, because we are asked for the heat capacity of the calorimeter, remember Q equals C delta T. That gives us, this is the heat capacity. So we're going to go C for the heat capacity and delta T. And this is the calorimeter. Okay, probably should have put in parentheses in the last one and didn't. All right, so let's start plugging in. So we have, the object is silver, so we have negative 200 and, excuse me, negative 275.0 grams. We're given silver's specific heat capacity at 0.240 joules per grams degrees Celsius, and the change in temperature, it started at 100 degrees and it ended at 28.5 degrees Celsius. Remember, it's going to be the same final temperature for everything. So it's negative 71.5 degrees Celsius. So I'm going to put that in here, negative 71.5 degrees Celsius. Okay. And then that, you know what, you could go ahead and do that because you're not missing anything, but we'll do it in a minute. Then we get the mass of the water, which we have 300 grams of water. And we're multiplying that by 4.184 joules per grams degrees Celsius. And the change in temperature for the water, we're told that the water starts at 25.3 and it ends at 28.5. 3.2 degrees Celsius, so we'll put that in, 3.2 degrees Celsius. Plus, we're looking for the calorimeter's specific heat, and we know the change in temperature for it is going to be the same as it was for the water. And so, if you go ahead and get this as one number, and then divide it by this, and then you're going to get that answer, and then divide it by this, you're going to get an answer in two significant figures. Are we down to one significant figure? Yeah, we are, so I'm going to have to show this to you. Okay, so this has three significant figures, so we've got this has three significant figures. And so it's going to be, what comes out of my calculator is 4719. So I'm going to put 4720, and that is going to be joules, and it's going to be positive because those two cancel one another out. So I've got this. This is 4.0 times 10 to the third joules. Okay. Plus C times 3.2 degrees Celsius. When I subtract this and this, which this is the significant figure, okay, the answer here is going to be 700, because it's 720, but my significant figures have to go to the least precise, which is to there. So it's going to be 700 joules. Okay, does everybody see what I did? I did this minus this, and it gives me 700 joules. So now I have 700 joules equals C 3.2 degrees Celsius. So I'm going to divide both sides by 3.2 degrees Celsius. And that's going to give me our answer. But this only has one significant figure. So my answer has to be in one significant figure. And so my answer has to be 200 joules per degree Celsius, because it has to be one significant figure, because that has one. and it was because of the adding or subtracting. 9, how much energy is required to melt 2.21 kilograms of copper? We are going to do Q equals the mass times the latent heat because we are melting something. So we're going to use that in this case. So we're going to go ahead and put in our mass, and this is in kilograms. So I'm going to go ahead and make this in grams. And then we are given we're trying to melt it, so we're going to use the latent heat for freezing. So it is 205 joules per gram. That's why we had to be in grams. Please notice this has three significant figures. So when you put in your answer, we get 453,000, and grams will cancel and we'll be left with joules. And so that's how much energy required to melt that much copper. How much energy is required to vaporize a 115 gram ice cube that is initially at the temperature of negative 11 degrees? Now remember, for this one, the first thing we have to do is get the ice cube up to 0 degrees, which is where it'll melt. So let's do the first step. Q equals mc delta T. Okay, so we have 115 grams, and we know that the ice has a different specific heat capacity. The ice, you see it on the chart, is, well actually it's told right here, is 2.093 joules per grams degrees Celsius times the change in heat. We're told that it started at negative 11.0 degrees Celsius, and we're bringing it up to 0 degrees Celsius. And so we already are subtracting this. So we're subtracting a negative, which is adding a positive. So this is 11.0 degrees Celsius. Okay, that's our first step. Please notice we have 3 significant figures. That first step gives us 2650 joules. There. First step, so we brought the ice cube up to 0 degrees. Now we're going to melt the ice cube, ml for freezing. Okay, so the mass of our water is 115 grams, and then we're given LF as 334 joules per gram. We have 3 significant figures in both places, so that is going to give us 38,400 joules. Okay, now we've brought it up to 0. Now we've melted it. Okay, so now we're going to take it up to 100 because we're going to vaporize it. So Q equals mc delta T. Here we have 115 grams, but now we're dealing with liquid water, so it's 4.184 joules per grams degrees Celsius. And the change in temperature was 100 degrees, where the final temperature was 100 degrees. Okay. So we can keep our 4 significant figures here. This gives us 48,120 joules. And now we want to vaporize it. So we're just going to go back to this one, the mass times the vaporizing. So we have 115. And the latent heat for vaporization is given to us. Grams will cancel. We'll be left with 4 significant figures. I'm so sorry. 4 significant figures. No, that's 3 significant figures. 3 significant figures. So it's going to give us 260000, but this one is the last significant figure. Now I realize we probably should write this 260 times 10 to the 5th joules, but then when I add them up, I'm going to have trouble. So I'm going to come over here, but you've got to watch your significant figures because when you add or subtract, you've got to go to the least precise. So I'm going to go 2650 joules, 38,400 joules, 48,120 joules, and 260,000 joules. And this is the last significant figure here. So my answer can only go to the significant figure there. So when you do these, you end up with an answer of 349,000, and you're going to have other digits, but you're going to ditch them because you have to go to the least precise, so these digits they'll disappear. Now if you actually do this, What you come up with in the calculator is 349,170. But once again, you're just gonna zero those out because you've got to go to the least precise because you're adding or subtracting. And in this chapter, more than any I've seen, you've really gotta watch the significant figures and take them with each step. Okay, go ahead and go over anything else you still have to do, study for and take this test. Have a Jesus-filled week.